Okay, thank you. It's great to be able to give this talk. I certainly wish I was there in person to give this talk. I look forward to the opportunity to be able to do so sometime in the not too distant future, maybe. It's also great to give this talk because these results have been a long time in coming. And it's taken a huge amount of work by a very large number of people to produce these results. So you see the two main results from the EHT on the left, M87, and on the right, Sagittarius A star. And I think you've probably all seen both of these results at this point. So here's M87, and this is the first image of a black hole. And, you know, the really critical or unique aspect of this is the extremely small angular scale associated with this image, 42 microarcseconds.
Sorry,
which is
the page is not changing. Oh, now changed. Sorry.
Oh, it did update?
Now updated.
Oh, okay.
Sorry. Yeah.
Okay. So 42 microarcseconds, which is about the size of an orange on the moon. And contained within that 42 microarcseconds is a 6 billion solar mass black hole. And here is Sagittarius A star. And this image is slightly larger, but really by a cosmic coincidence, almost the same size within about 25%, 52 microarcseconds in diameter. Sagittarius A star is the Galactic Center black hole, the Milky Way Galactic Center black hole. And you can see the mass contained within that ring of light is 4 million solar masses, about 1,000 times less than what's contained within the light ring of M87. So in this talk, I'm going to tell you about how we obtain these images, why these are our two targets, what we've learned from these images, and where we hope to go in the future with the EHT and our measurements. Because this is the theory seminar, I'm going to try to put a little bit more emphasis on the theory side, but I am not a theorist, and so you will get my my spin on the theory. Feel free, of course, to ask questions as we go. I can't actually see things like raised hands or if people are waving, but feel free to speak up and say something and ask a question. So these images are really the results that launched 1,000 memes, and maybe the most special of these to me is the XKCD comic. First off, because XKCD is really cool, and second, because in its fashion, it teaches us something about the image as well, right? That image of M87 is comparable to the scale of the outer solar system. Whereas for Sagittarius A star, not shown here, the image diameter is comparable to the orbital radius of the planet Mercury. So that gives you a sense of the overall scale. As I said at the outset, this is work done by a huge number of people. The Event Horizon Telescope collaboration is now over 350 members in over 24 countries and regions around the world and dozens of institutes. This is the collaboration photo from the last time we were all together in one place in 2019 in Hilo. I'm sure many of you recognize this location. Definitely a big part of the challenge in producing these results was through doing this work virtually. And so this is what collaboration meetings have looked like over the last 2.5 years since then, where we've met online. I can tell you that solving complex problems among hundreds of individuals is extremely challenging to do in a purely virtual environment. And that is why these results took as long as they did to come out. The other part is simply that we put a huge amount of care into the work. I do want to emphasize a little bit the contributions from Taiwan and essentially ASIAA to this work. We are partners in 4 of the facilities that contributed to EHT work, the SMA and the JCMT, which have a long history of being involved in this work. ALMA, which of course has really transformed our capabilities because of its sensitivity, and the GLT, which didn't contribute to this work, but the GLT team, who you see here, did make major contributions. And you also see the many of the local team members here in Hawaii who contributed to this work. In addition, this is really a long-term interest of ASIAA. 3 EHT directors have played a role, or 3 ASIAA directors have played a role. Fred Lowe, of course, did some of the earliest observations of Sagittarius star, and Paul, we all know, has played a huge role. And Wei Li is an EHT member and contributor as well. And so I also want to emphasize some of the technical contributions, in particular Ho-Min's work on digital analog to digital converter cards provided a technology that is installed at all of the EHT facilities around the world and is central to our ability to carry out this work. So really, this is a huge effort that's been achieved as the result of many years of effort and investment in facilities and people. Okay, so Sagittarius A star and M87 are our 2 targets. Why is it that those are the 2 main targets? Well, the shadow diameter is roughly 10 times the gravitational radius. And a priori, we can predict that to be on the scale of tens of microarcseconds based on other measurements of the mass and distance to these 2 objects. And it turns out that both for Sagittarius star and M87, well, both Sagittarius star and M87 are the 2 objects that are the largest black holes on the sky in terms of their angular size. And in a very fortuitous set of circumstances, they are also among the brightest of black holes at millimeter wavelengths, where we achieve our highest angular resolution. There are other EHT targets that we have observed. Some are a little bit brighter. There are blazars like 3C273. And there are other AGN or black hole systems that are, are perhaps partially resolved by the EHT or will be resolved by the EHT, but not at the shadow scale, at least as we know it right now. So Sagittarius star and M87 really do stand out as the two most important targets. It's been known for more than 2 decades that Sagittarius star is an excellent target. This is from a paper from over two decades ago, predicting the shadow size and appearance, and predicting a diameter of around 50 microarcseconds. And that prediction comes from some fairly straightforward physics that goes back actually even beyond what I'm showing here. But Bardeen in 1973 showed that essentially that the shadow is the impact angle of photons that are just outside of the photon orbit. That's that 3 circle that you see there, the orbit at which photons the radius at which photons will orbit the black hole. And just outside of that, photons get lensed into this ring, which is about 10 times the Schwarzschild radius, 10 times the gravitational radius. The first simulation predicting an image was made by Luminet, and it was a computer simulation, but the rendering here is actually a hand drawing based on the output of that simulation, because he actually lacked the any capability of doing a computer rendering of his simulation results. It's certainly a testament to how far this science has advanced in 40 years. So there's been an industry of this kind of simulation over the past few decades, and this set of movies is one example of this. And so this is showing an accretion flow that also produces a jet, and showing that at 4 different wavelengths: radio, millimeter, infrared, and X-ray. And you can see at long wavelength radio, the system is optically thick, and we don't see the shadow feature, or it's only present some of the time. At millimeter wavelengths, it's optically thin, and we're able to see all the way down to the shadow, and the shadow is a persistent feature that's present there. That feature is also present at infrared and X-ray wavelengths, but of course that's unobservable, with present day technology. There are no instruments that can achieve that angular resolution. So this is, before I move on to talking about the Galactic Center in detail, this is normally where I would say something about the observational challenges and techniques associated with this. So in the interest of time, I'm going to skip over most of that, but I'll just say that, this was a major effort to organize the observatories, develop new technologies, and have expert observers and instrumentalists who prepared the observatories and were present for the observations and committed enormous amounts of their time and careers to make this work. So now I want to turn to the Galactic Center and talk about what's special about the Galactic Center and what we've learned there. So this is an infrared view, optical infrared view of the Galactic Center, and Sagittarius A star is located here in the Milky Way center, the nuclear star cluster. And of course, the study of stars in the Galactic Center led to the Nobel Prize for Reinhard Genzel and Andrea Ghez 2 years ago for their work studying the motions of stars around Sagittarius A star. And that work is so exquisite now. There are now 4 stars whose orbits around Sag A star are constrained and are used to measure the mass and the distance of Sag A star to a precision better than 1%. That's this plot in the upper right from the gravity group, showing the incredible precision in black hole mass and distance to the Galactic Center. And of course, the S2 star is the most famous of these, shown here in red, with a 15-year period around Sag A star. Now, one of the interesting details about this work is that while the results from the 2 groups have a precision of better than 1%, their accuracy is somewhat less. There is some uncertainty or systematic difference between the Keck and the VLT measurements that you can see here in the bottom right at a level of a few percent. That's a testament to just how exceedingly hard it is to make these precision measurements over long periods of time. That discrepancy doesn't affect our results because, as you'll see, our overall uncertainty right now is more on the scale of 10% rather than a few percent. But in the future, that could become an interesting factor. So now I want to show you this movie of the radio view of the Galactic Center. So you see the galactic plane in radio, and now we're going in towards Sag A star, and that we're in Sag A East right now, which is a supernova remnant, and that compact knot is Sag A star itself, buried amidst all of this material. And that should give you a sense of how weak a black hole that Sagittarius A star is, right? That it really is totally the Galactic Center radio emission is totally dominated by these other features that are present there, and there isn't any large-scale jet that's obviously associated with Sag A star. There's some evidence of feeding material down towards Sag A star, but still extremely hard to characterize or explore that in any detail. And this is one of the great things about having this kind of result, is that you get people who put a huge amount of effort into these kind of great graphics to demonstrate these results. So how did we come about making this image? Well, This is what the state of the art looked like a decade ago. Interferometric observations using the JCMT, KARMA, and the SMT. A three-element interferometer, we're able to resolve out Sagittarius A star and give a characteristic size of a few Schwarzschild radii. But there was no hope of being able to make an image from this data. Right, so I'll take a moment here to talk about how an interferometer works and what these measurements mean. An interferometer on each baseline, each antenna pair, measures one component of the two-dimensional Fourier transform of the image brightness on the sky. And if you have a filled-in mirror, you're capturing all of the Fourier components, and that instantly gives you a perfect image. If you have a very large number of antennas, then you have some approximation of a filled-in mirror. And then VLBI uses what we call Earth rotation synthesis as well, that as the Earth rotates, those antenna pairs, as viewed by the distant source, are selecting different Fourier components and filling in that mirror. There's no hope of filling in the mirror when you only have three baselines to make the measurement, and the only thing you can do is model this data. And in this case, we take the Fourier transform of a Gaussian, which is what the data look sort of like. Fourier transform of a Gaussian is a Gaussian, so you can measure an angular size by making that assumption. The data could have been fit or were fit by a ring model, but we certainly did not have the confidence to claim that was an actual detection of a ring. In the intervening years, there's been a pretty substantial improvement in the capability of imaging. And before the release of our latest image, of our 1.3 millimeter image, this was the highest quality image obtained of Sag A star. So this was at 3 millimeters using the VLBA and other stations. And it's a fuzzy blob. There's very little structure associated with this. Why is it a fuzzy blob? It's a fuzzy blob because there is angular broadening that's due to interstellar scattering along the line of sight. And that interstellar scattering just comes from turbulent plasma, maybe in supernova remnants or H2 regions that are along the line of sight. We've known about this effect for decades because Sag A star has this incredible appearance that as you go to long wavelengths, its size scales exactly as wavelength squared. And only as you get to the shortest wavelengths does it deviate from that. That wavelength squared is purely the effect of this interstellar turbulent scattering. This is a part of the cosmic coincidence that makes 1.3 millimeter observations of Sag A star effective, is that we are in a regime here where the scattering contribution is negligible or is very small, at least. This is just an illustration of that effect. It also affects pulsed radio waves, such as from a pulsar. It's the same effect that broadens the pulse of a pulsar will broaden the image of a continuous source. Now here are the 2017 observations. And you can see that we now have many more stations and we have a much more filled in UV plane or aperture plane that allows us to have the confidence to make an image out of this. This is the visibility amplitude data that comes from that. So this is the comparison point to make is back towards that visibility amplitude plot that I said we did a Gaussian fit on. Now I like to show this because even though, so, you know, if you're not an experienced radio interferometrist, you might think that the algorithms that we use to make images are a little bit of, you know, black box voodoo, you know, something that you don't understand, highly processed results. But if you understand Fourier transforms, then you can understand the argument why we think we have, why we claim to detect a ring in this data. So the dashed line that's shown here is a Bessel function, and it's which is the Fourier transform for a thin uniform ring of a diameter of about 50 microarcseconds. And you can see two really key features, well, several key features. You can see the fall off at short interferometric spacings, and you can see the presence of two nulls in the visibility domain coverage. Those nulls are really important in terms of characterizing the diameter of the ring and whether or not it is a ring or a filled-in disk. You can also see that the data is somewhat imperfect in that it doesn't perfectly follow this Bessel function curve, and in particular, some baselines here, for instance, do not go all the way, do not go down into the null, and there are other discrepancies or uncertainties. That tells us that there's more information here than just a simple ring, and it points to asymmetry, and it also points to time variability, and I'm going to talk about both of those as we go further on here. So the two key challenges in imaging were on dealing with scattering and time variation. Scattering really turned out not to be a significant effect. We explored imaging with and without the methods for compensating for scattering, and we really don't see significant differences there. Temporal variations, on the other hand, though, are real. You can see the light curve of Sag A* during these observations, oscillating along here. And then this is a somewhat technical measure, but it's what we call a closure phase, and it measures something about the structure of the source that's independent of calibration and independent of time. And we can show very consistently between two different days that the structure of the source has to have changed. So over a 24-hour period, we see very obvious indication of structural changes. And that tells us that, of course, over the roughly 12-hour time period in which we're making our image, that it's likely that the source itself is changing as well. And we have other ways of characterizing that variability, but that's a kind of straightforward argument for that. So I'll move on from this point. So why is it that that Sag A* is so much more variable than M87? Well, that's because Sag A* is 1,500 times less massive. And so its physical scale is 1,500 times smaller. than M87. M87 has a characteristic time scale measured in tens of days, and Sagittarius star has a characteristic time scale measured in tens of minutes or hours. So over the time scale in which we're trying to make an image, the image of Sagittarius star itself may be changing. So this is just another visualization of that variability. You can see Sagittarius star sitting in the mini spiral here. This is real data as observed by ALMA. And you can see Sagittarius star fluctuating during the course of our observations. The 2 days that we analyzed in these papers, the variability was more modest, was on the order of 10% RMS. There's actually a day that we didn't publish results on that's very exciting, and we're looking at now, in which there was a Chandra X-ray flare that occurred immediately before our observations. And then you see really significant variations in the millimeter light curve. And potentially that couples with interesting dynamics. But we wanted to keep to as simple a situation as we could for this first imaging paper. So one of the techniques that we made use of for how we studied or we dealt with this variability was essentially to decompose the result into a static image and a time variable residual, and we attempt to characterize that residual. So we made a goal of obtaining a static image that's that's unaffected by time variable residuals. And so this is a simulation, and this is not intended to give you a seizure, but it's intended to demonstrate for you what in visibility space this variability looks like. And what you can see is that those residual fluctuations, you can think of that as producing a kind of characteristic variation or characteristic noise floor in this regime that we can try to account for with our imaging techniques. And so we studied GRMHD simulations, and we also characterized our own data. And that allowed us to create a prescription for how much noise we think gets introduced into the system by variability. And then we use that as a part of our imaging algorithms to essentially suppress the effect of variability. The other technique that we use is simply to take snapshots of the data. So we can't make images on very short timescales because our aperture information is incomplete. But we can model rings on short timescales. So here are some of the images that we made, and I won't go into all the details, but the key point here is that we used a really wide variety of methods. We considered with scattering and without scattering, and we have 2 different days. And all of this comes up very consistent with a ring of about 50 microarcseconds in diameter. It turns out that it's not perfectly associated with that. And some fraction of the images that we reconstruct, a couple of % have characteristic sizes of about 50 microarcseconds, but do not resemble a ring, or you have to use your imagination a little bit to recover a ring from that data. So we can't rule out the possibility that these are correct images, but they are very unlikely. The other thing is that these bright features that you see in the image you really can't trust those. These are not hotspots that we think we can robustly, say are located. This isn't the result of a hotspot that's moving around and we're capturing it at a few different times. We really, at this point, we would best characterize these as imaging artifacts, and we see these in simulations. That we produce these kinds of effects when we introduce real effects into our synthetic data. Okay, I think I'll move on from this. So now we measure a diameter, 52 plus or minus 2 microarcseconds. What do we do with that in order to tell us something about the astrophysics and the black hole physics and the general relativistic physics of this system? Well, we have to calibrate that diameter against a number of effects, but a dominant one is simply that we want to get at something like the photon ring or the black hole shadow, which are mathematically defined quantities. How do we get to those? Well, we have to calibrate against real astrophysical models that fold in our uncertainty about accretion, jet formation, the inclination angle of the system. And you see some of the different models that we use here for doing those calibrations. And in the process of doing this, we go from about a 5% uncertainty in the diameter to about a 20% uncertainty in the gravitational radius or in the mass of the black hole. So our uncertainty in the mass of Sagittarius that we can derive from our measurement is dominated by our uncertainty about the astrophysics of Sagittarius A star. Okay, so I think I've made most of these points here, so I think I can move on from that point. But this is really intended to kind of, put you in the, give you a firm understanding of what the overall limitations are in these measurements, or what you can trust in them and what you cannot trust in them. All right. So now let's talk about the astrophysics and what we can say about the astrophysics from this from the comparison with the data. So we ran an enormous ensemble of GRMHD models and ray traced them. So we look at inclination angle, black hole spin, retrograde and prograde. This R high parameter is a parameterization of the electron to proton temperature. We also do MAD and SANE models, which is a way of characterizing the significance of magnetic fields. And these are all time-dependent models. MAD, as many of you probably know, is magnetically arrested disks. SANE is standard and normal evolution. So those have weaker magnetic fields. You can see there's a wide variety of phenomena. We also explore things like non-thermal particle distributions. We use different modeling codes and some other special cases. And then we compare those models against astrophysical constraints, so the EHT constraints themselves, as well as the rich multi-wavelength data. And the EHT morphology information, the ring diameter, and the presence of the shadow, and a constraint on the width of the ring are really strong constraints. Or maybe I'll run this again, just so you show. So this is selecting models based on different parameters. And so size, this is a very broad measurement of size, not the precision measurement of the diameter. And here's where the EHT measurements themselves do a huge amount of selection. And then the multi-frequency spectrum, the 86 gigahertz size, 3 millimeter size. And we get down to a very small number of models that pass constraints. And actually what is truly remarkable is that none of the models, none of this enormous ensemble of models that we use actually satisfies all of the constraints. A really difficult model or constraint to satisfy is variability, just variability of the light curve. The GRMHD models tend to produce more significantly variable light curves than what we actually observe. And so if we remove that variability as a constraint, we come up with a handful of models which we think are a reasonable set of constraints, what we call our best bet. But I like to think of it more in terms of what we think are strongly disfavored. And so edge-on systems, retrograde spins, and situations where the electron temperature is equal to the proton temperature. So these are radiatively inefficient accretion flows. But that low inclination angle, at least not edge-on, is certainly very interesting. It says that the inclination angle is not aligned with the galactic plane. It's also interesting in that it is appears to be consistent with the results from the gravity measurements with the VLT, where they measured just the change in the centroid position of Sagittarius star and argue that that's the result of a roughly face-on system of a comparable diameter to what we measure. So that's certainly very interesting and something that we expect to explore further in the future. Now let me go on to the general relativity, gravity physics, and black hole physics. So this is a phase space plot on the left of different kinds of general relativistic tests. And so we have the gravitational potential, V over C, roughly, and then we have the space-time curvature. And so stellar black hole and neutron star mergers, as measured by LIGO and Virgo, are up here in this corner. We have solar system tests here, very low potential, and comparable curvature to supermassive black holes. We have cosmological probes that exist at this other extreme. And so the EHT measurements, and I think it's really important to emphasize, exist in a parameter space that no other measurements are in. And they span a really wide scale here, right? 6 orders of magnitude in curvature as a result of the the mass difference between Sag star and M87. So these are all complementary measurements of this vast parameter space. The other thing is that the measurements also probe different kinds of physics. So there's dynamical and stationary space-time metrics. We're in the stationary regime, whereas at least some of what LIGO does, for instance, is in the dynamical metric, because you have the actual evolving system. And then there's metrics that involve matter and metrics that are vacuum metrics. And so there's a really complex landscape of the different kinds of tests, and where we sit in a unique part of that space. I want to talk about one, I think, really interesting set of tests that we did, which ties nicely to the astrophysics, and that is a question you can ask is, what can we say whether or not there's an event horizon? And one could imagine, say, instead of a surface in which material passes through the event horizon and adds to the mass, but is otherwise never detected again. Imagine a situation where there's a hard surface. The event horizon is replaced by a hard surface, material rains down on it, and that surface heats up as a black body. And so that produces emission that will appear in the ultraviolet or the X-ray. Our EHT measurements set a size scale for how what an upper limit on the size of that surface, and so that affects the overall temperature that you can predict, and we can show that any plausible model is inconsistent with an event horizon. On the right, we explore models of not an absorbing surface, but a reflecting surface. So imagine that the radiation that is produced outside of the event horizon is somehow incident on the event horizon surface, but that surface is reflective of millimeter waves. And you can ray trace that and make predictions about what kind of image we would see. And so these are images for different albedos, and then synthesized into an EHT type of image. And we can rule out something greater than about a 30% albedo from this data as inconsistent with the images that we obtain. Now, one of the meatiest aspects of this work is just to make a comparison against the prediction of the Kerr metric. We did this for M87, and you can see and this is purely based on the diameter of the ring that we measure and then calibrated against the astrophysics of the system. For M87, we have this, we had two different a priori measurements from gas and stellar dynamics. If you believe the gas dynamic measurement, then something is really wrong with the Kerr metric. If you believe the stellar dynamic measurement, then we have very good consistency with Kerr. And the same holds up for Sag star, where we have this extremely precise prediction of the shadow diameter from that 1% m over d. And we have very good consistency there. And so that's a really important part of the significance of Sag star, is is that precision measurement and of M over D that we can compare against, which we don't have for M87. We also do some comparison against non-GR, non-standard black hole models, and do some ray tracing of these. And these are just some of these examples. So for instance, boson stars do not give you a predict a shadow, and some models predict different diameters. And we can kind of put all of that into a kind of parameterized framework for many of these different types of models, and rule out certain parameters that will apply to this universe of alternative black hole and alternative GR extension type models. It's extremely hard to rule out any one particular class of these because they all tend to be parameterized systems, but we can place constraints in this space. Okay, let me just say very briefly a few things about where the EHT is headed. So you may remember a year ago we put out a polarimetric image of M87. Sagittarius star is very highly polarized, linearly and circularly polarized, and so we're quite interested to explore what we can see with Sagittarius star polarization. M87 and Sagittarius star we expect to be dynamic. In the case of Sagittarius star on the time scale of hours or even less, M87 on longer time scales. And so we are interested in the time domain measurements of these sources. These are some proto constraints that we placed on M87 after we made our image, our 2017 data image, and went back to old measurements and showed consistency in the ring diameter. We hope to do this in a much more satisfactory way in the future with higher quality measurements. And we have a lot of data. So both the Sagittarius star and M87 results are from 2017. We have 2018 data that we are working on very hard right now. This has the GLT as a part of it, observing M87, and so that's going to be quite interesting. We didn't observe for 2 years, but we have observed for the last 2 years, and we've added new stations, so that's going to improve our ability to do, perhaps to make movies of Sagittarius star on short time scales, also to make high quality images of M87, potentially detect the jet associated with M87. And then we're looking to the future where we've put in our proposals to observe for next year. We'd like to observe at 345 gigahertz. And we're looking to future years beyond that to have higher fidelity images, make long-term movies, and explore the evolution of these systems. I think I'll skip over this, but there's a huge amount of technical development and dreaming about where this can go over not just in a few years, but 5 years, 10 years, 20 years from now, even going into space. So let me sum up. A few key results really to focus on here. Black holes power active galactic nuclei. This is a 60-year-old question that we have answered. At the base of those powerful jets sitting in distant radio galaxies, there is a black hole. in the nuclei of normal dormant galaxies, low luminosity AGN, there is a black hole sitting there like Sagittarius A star. We're testing general relativity and black hole models over 3 orders of magnitude in mass, and providing really unique constraints. And we are pushing the boundaries for accretion and jet physics, and making precision measurements in that space. And so there's a huge amount to come in those areas. So I'll stop here, and I'm happy to take some questions.
Are there any questions?
Hi, Geoff. This is Yanting.
Hi.
So you mentioned that gravity instrument has measured like the inclination consistent with the EHT result, but your resolution is, I don't know, 1,000 times better than theirs. So how could they claim that? I mean, how could they measure or estimate the inclination of the black hole?
Yeah, that's a great question. So when I first heard Reinhard Genzel predict that they could make this kind of measurement, this was before the VLT, or before the gravity instrument was commissioned, I really thought it was impossible. It really is on the edge of what they can do, but what they do is they measure over a short period of time the astrometric position of Sag A star relative to their reference stars, and so they're able to achieve an astrometric accuracy that is 100 to 1,000 times better than their imaging resolution. It's really incredible, right? In order to achieve that, right, that means that they have to have a signal to noise of about 100 to 1,000 times better, and control of the systematics of the astrometry at that accuracy. They have one published results of this. I would very much like to see it repeated. I don't think that Keck has the capability to repeat this measurement with their AO system, but perhaps with a future AO system it could be repeated. And maybe there are other ways to test it. So it is a really astonishing measurement to see from that instrument.
Okay, thank you. I have another question. So the Fermi bubbles show that I guess once before the black hole spin at least was perpendicular to the galactic disk. So how easily do you think is the spin of the black hole to be tilted or changed?
Yeah, that's a good question too. I asked some people who are experts in, black hole evolution over cosmic time, and I asked them, what do the models tell us about the the history of black hole spin, and they just laughed. I think that the short answer is that it probably takes giga-years for the spin to change significantly as a result of accretion. Of course, mergers would change it more rapidly. But so there's a more prosaic astrophysical way of addressing this question, though, which is that the localized spin, or the spin of the black hole, right, is tells you, what orientation material will get ejected from the system. And that holds up on the small scale of where the black hole has, its gravitational sphere of influence. But that is a very small scale relative to the scale of the Fermi bubbles, or relative to the scale of, M87 jet, for instance. And so other factors such as the pressure profile or the magnetic field profile in the center of the galaxy are what will determine the large scale orientation of an outflow. And the black hole spin really only determines the local orientation of the outflow.
I see. Okay.
Yes, black hole spin direction is determined by long-term Sgr by long-term accretion process, for example. However, the present accretion disk angular momentum direction is determined only the current accreting process. So they may be very different indeed.
Yeah, that's right. That's another aspect of this and we think that the accretion onto Sagittarius is most likely coming from material that is ejected in stellar winds from the cluster of stars orbiting Sagittarius, and that is roughly an isotropic distribution of stars. And so it may have some angular momentum, but we expect a kind of quasi-spherical accretion until you get down to the smallest scales around Sagittarius.
So like a boundy like accretion.
Mm-hmm.
Then
exactly, like Bondi type accretion.
So the fact that both N87 and Milky Way black hole are kind of facing us, is this a weird coincidence?
Well, I would first say the M87 is at an inclination of we think 17 degrees. That's the kind of nominal number. For Sagittarius, we are, I would say the constraint is, that it's not edge on. So I don't think I don't think we've really excluded a huge amount of the possible inclination angles. And so I would be cautious about, don't think of it as, the jet is pointing right at us. It's really just that it's not obvious. It's not an edge-on system. So I don't think there are any obvious selection biases here. Neither of the sources are, so pointed towards us, at least as far as we know, that we're getting really significant Doppler boosting that makes them brighter. As you go to, if you look at blazars, right there, the high redshift radio sources that we know are almost all, beamed within a few degrees towards us, and that gives a Doppler boosting, which brightens the emission.
If the jet is pointing toward us, then gamma ray observation also constrain, for instance, the viewing angle and so on. And so I consider that collaboration with other wavelengths, such as gamma rays particularly, both radio and gamma ray emissions are emitted. They are primary emissions emitted from the direct vicinity of the black hole, unlike X-ray or opticals. Well, X-ray and optical photons are emitted, reprocessed and emitted at greater radius from the black hole. However, radio and gamma ray emissions are emitted from the direct vicinity of the black hole. So I think collaboration with such as CTA, Cherenkov telescope array, may be very helpful to constrain the emission model of black hole vicinity.
Yeah, that's a great point. You know, we do have we do use Chandra X-ray observations, and we do have some contemporaneous measurements, not from this campaign, but I think from other campaigns, of very high energy gamma rays. It would be great to, from some of the ground-based detectors, it would be really great to be able to show a clear connection between the, you know, the gamma ray emission that's detected and variability in the X-ray or the millimeter that we could clearly associate with Sagittarius star. You know, the big challenge for Sagittarius star is that, you know, there's all these other emission sources in the galactic center, X-ray binaries, supernova remnants, that also produce gamma rays. And the gamma ray instruments are all very low resolution. So it can be difficult to separate out the source of the emission, but it's still a powerful constraint.
Okay, thank you very much.
Are there any questions? Okay, thank you very much, Geoff, for presenting us very important and exciting results of EHT. We very much enjoyed your talk.
Yeah, Koichi.
Okay, great. Thank you all.
Geoff, hold on. Geoff.
Oh,
Geoff?
okay.
Hi,
Yes.
Geoff. I do think you have this presentation will be very useful, because I think one of the purpose of this talk, this series of talks will be motivate people working on different areas in the institute, so especially students. So, Koichi, I think we should leave a few minutes to encourage students to raise hands, because they probably have been really awed by Geoff's talk. Okay.
Yeah,
so
I'm certainly happy to take more questions. I'm summarizing about 400 pages of papers, and so there are a lot of details that I have left out.
So, students, are there any questions?
Any people, I think there are a lot of students who are interested in black hole physics and all the exciting results you guys present to EHT, you know, and our own colleagues. But then I think people are usually afraid of asking these difficult questions, because every time they talk about black holes, they say, well, okay, I think black holes so amazing, but then they don't know how to ask questions.
Yeah. Well, Sienna, what question do you think is on the mind of a student who saw this talk? Maybe you can pose a question for them.
Okay, so let me ask question backwards, right? As you saw, as you put in the last slide, you did put in what you've done for EHT and what you expect for the future at EHT. So I suspect, I think what you mean by next for EHT, next generation EHT and the like, right? Or you are actually, okay. So you put a lot of new items.
Yeah.
So what do you think, for example, let's ask a forward-looking question. What do you think, what you've done so far, which 400 people's work, and what have been solved, what have not been solved? Gives some forward-looking prospects for students who are still staying this talk.
So I think one of the really interesting things that came out of the theory side of the Sagittarius star work is this fact that that the variability is over predicted by theory. And, you know, so as an observer, there's nothing I love more than being able to tell theorists that they're wrong.
Thank you.
Of course, we also love to be able to find the really great predictions that theorists make. But so this is a really, you know, it's really instructive, I think, that, you know, this really broad range of theoretical models that we constructed to try to explain the data, you know, was insufficient. It's incomplete. There's physics that we're not putting into the theory, into the simulations that's required by by reality. What is missing there? Well, so it may be that, you know, and this goes to Sienni, what you and Koichi work on, of that the extremely small scale of particle acceleration and particle energy distribution actually has a really big effect on or determines the electron energy distribution, which determines the degree of variability. So I think that's kind of a wide open area where I think a lot of people could contribute. You know, as an observer, for me, I think, you know, what's the next most powerful and obvious thing to do? We have all these beautiful simulations that show the time evolution of these systems. Let's make a movie. Let's see the let's see the evolution of these systems over time, and try to understand what that means. In a really long time scale, I think that getting higher angular resolution is really compelling. And there are two ways to do that. One is to do it from the ground by going to much higher frequencies, and the other is to go to space and get much longer baselines. And there are two reasons to get higher angular resolution. One is that we can see finer features in the image, right? One of the questions that we get is, why is it so blurry, right?
Yes.
You see a few blobs, but it's not blurry. It's very sharp. It's just very zoomed in. But we want it to be, we want to see all that really interesting, intricate structure that the theory predicts, which we do blur out because we're right at the edge of our resolution. So that's one thing. The other thing, and there are some really interesting predictions, not just of astrophysics, but of general relativity, of the kind of nested rings of lensed photons that you see, doing multiple orbits around the black hole before they come out. The other really interesting thing to do is to get more objects. Higher angular resolution, we can look at, there's a wider sample of objects that we can detect and study. Centaurus A, for instance, M81, M84, and then use this to study black hole masses, black hole spins. So this really is just kind of the beginning of what we think we can do.
So you are saying that you are actually the foundation work that EHS layout will be ready for next generation to take out for many, many years of work.
Yeah, absolutely. Yeah, this is this is our first step, and there's a huge amount to do for years and decades to come. For the students and for the postdocs who are looking at this and thinking, wow, this is really cool. I want to do this. If you're an observer, if you're an experimentalist, if you're interested in Bayesian data analysis techniques, or if you're interested in simulations, or you're interested in, pencil and paper, GR theory, there's a huge amount of work to do in all of those areas.
Okay, thank you. I think everybody will be very encouraged by your statement.
Yeah, good.
Thank you. This huge congratulations to you and your whole project. And I know Satoki is online. Satoki, thank you too for your team. And thank you everyone who's here. And Geoff, this is amazing amount of work. And the perspective you gave today will be very helpful for anyone who's in the talk or anyone who's watching the video.
Yeah, thank you very much. And it really is my pleasure to give this talk on behalf of the whole collaboration. I can't emphasize enough, how much members of the Institute have contributed to this work. Satoki has, Keiichi, and many others have been at this for a long time as well.
Yeah, so this is a truly an example of teamwork.
Yes.
Really, thank you. Huge congratulations. Yeah, we all should feel proud too. Okay, thank you.
Okay, all right, bye-bye.
Thank you very much. Bye-bye.